Okay, so we start a new chapter today, and we'll be discussing atomic structure in the periodic table. So we'll begin with a discussion of the internal structure of the atom and the particles that make up atoms, and then we'll discuss two numbers which describe the internal structure of an atom, namely the atomic number, which describes the number of protons and electrons, and then the mass number, which describes the number of particles that are in the nucleus of the atom. This leads us to be able to describe what are known as isotopes, which are atoms of the same element that have different numbers of neutrons in their nucleus, and then how we can calculate what is known as an atomic mass, which represents the mass of an average atom in a sample of an element. To do this, we're going to calculate what's known as the weighted average, and I'll guide you through that process. So the understanding of the structure of atoms and the qualities of atoms gives rise to the modern periodic table, which was based upon the observations of Mendeleev and his observation of the periodic law, and then that is encapsulated in the periodic table. We'll then look at how elements can be grouped within the periodic table into characteristics of metals and non-metals. So it was John Dalton who used the observation of other scientists and his own to formulate the first modern atomic theory, and his theory was based around four ideas. First of all, in common with Democritus and some of the earlier philosophers we talked about earlier, he stated that all matter is composed of tiny indivisible particles called atoms. Furthermore, he said that atoms of one element cannot be converted into atoms of another element. So this eliminates the possibility of the concept of transmutation, which alchemists had been working on for many years. That is the idea of being able to turn a base metal into a precious metal such as gold. He then formalizes the definition of an element and says that atoms of a given element are identical to each other. And then formalizing the definition of compounds, he says compounds result from combinations of elements, and in these must be different elements, and they are combined in specific whole number ratios, which makes sense. A specific ratio indicates a specific compound, and there must be whole number ratios because atoms are indivisible. So while modern theory at times diverges from Dalton's ideas, Dalton's theory has been enormously successful and explains a huge amount of the chemistry that we observed and is still used extensively today. However, where modern theory does differ from Dalton's ideas is that modern theory considers the atom to be comprised of two key parts: a dense nucleus, which contains nearly all of the mass of the atom, and that mass is in the form of two particles, neutrons and protons. And then at great distance from this nucleus are small negatively charged particles that have very little mass called electrons. So within the nucleus we have protons and neutrons. The protons are positively charged and the neutrons have no charge. Protons and neutrons have similar mass, which is about 1 atomic mass unit, where 1 atomic mass unit is very small unit of mass. It's 1.67 times 10 to the minus 24 grams. Now for a proton we give it the symbol P, or sometimes a P followed by a superscript plus, and for neutrons we will often give them the symbol N. Electrons are not in the nucleus. They're at quite a distance from the nucleus. They have a charge that is of the same size as the charge on a proton, but is opposite in charge and is negative. And electrons have very little mass. It's approximately 1/2000th the mass of a proton. And electrons we give the symbol E followed by a superscript minus sign. So it was Ernest Rutherford who was the first scientist to determine the size of an atom and its nucleus. And he determined that the nucleus of an atom occupies only 1/100,000th of the volume of the atom. That is, in the middle of the atom we have a very small nucleus that contains effectively all of the mass, and then at great distance from the nucleus we have the electrons, which have very little mass, and in between it's mostly empty space. So most of all atoms, or in between, is empty space. So most of all atoms, and therefore most of all matter, is empty space. So this idea of electrons moving around at great distance from a very dense nucleus is called the planetary model, or sometimes called the Rutherford model. And the most important thing to recognize is that when atoms will interact with one another, they will do so through their electrons. It is the electrons that comprise the outer surface of the atoms. So the chemical properties of an atom are going to be determined by the nature and number of electrons that the atom has. So as atoms have no overall charge, they must contain the same number of protons, which have a positive charge, as electrons, which have a negative charge. So we give the number of protons in the nucleus of an atom the symbol Z, and we call that the atomic number. And so it's the atomic number that determines the number of protons and therefore the number of electrons. So atoms of a given type or of a given element have the same atomic number. And furthermore, atoms with the same atomic number will have the same number of electrons, and therefore they will have the same chemical properties, because it is through their electrons that atoms interact. So neutrons have no electrical charge. They do not influence the number of electrons that an atom will have. Therefore, for a given atom type, which is determined by the number of protons and the number of electrons, the number of neutrons may vary. So atoms with the same number of protons but different numbers of neutrons in a nucleus, we call these isotopes. So for example, there are 3 naturally occurring isotopes of hydrogen. The most abundant is that which has simply a proton in the nucleus and no neutrons. But then there are 2 rarer forms, one form which has 1 proton and 1 neutron in the nucleus, and an even rarer form which has 1 proton and 2 neutrons in the nucleus. The isotope with one neutron in the nucleus and 1 proton is known as deuterium, and the isotope with 2 neutrons and 1 proton in the nucleus is known as tritium. So the same number of neutrons and protons in it, the sum of the number of neutrons and protons in an atom is called the mass number, because all of the mass is in the neutrons and the protons. And we give the mass number the symbol A. And as we stated before, it is the number of protons which determines the atom type, but it is the sum of the neutrons and protons that determines the mass. Given the mass number and the atomic number, it is possible to calculate the number of neutrons. So the number of neutrons is simply the mass number, number of protons and number of neutrons, minus the atomic number, which is the number of protons, which leaves us with the number of neutrons. So we can use the following notation to indicate any atom and what its nucleus is composed of. So we write as a preceding superscript the mass number, and as a preceding subscript we write the atomic number. And then this is followed by the symbol of the element, which is either a single uppercase character or an uppercase character followed by a lowercase character. So for example, this is how we would write the isotope of carbon that has 6 protons and 6 plus 6, a total of 12 particles in its nucleus, so a mass number of 12. This is how we would write the isotope of carbon that again has 6 protons, because every atom of carbon has 6 protons regardless of how many neutrons, and then it has a total of 13 particles in its nucleus, a mass number of 13. So this would have 7 neutrons, 13 minus 6 in its nucleus, and we can do that for any isotope of any element. Now, as every element of carbon will always have 6 protons, that's what makes it carbon, and every element of hydrogen will always have 1 proton, that's what makes it hydrogen, there really isn't any need to write both the atomic number and the symbol. So what people will often do is skip writing the atomic number, because that's identified by the symbol. So we'll drop that lowercase number here. And then we will write that like so. This would be carbon 12, so this is a carbon atom with 12 particles in its nucleus. This is a carbon atom with 13 particles in its nucleus. And we say this in words, carbon 12, and this carbon 13, and this carbon 14. This has 6 neutrons, 7 neutrons, 8 neutrons, because carbon has 6 protons in its nucleus. Okay. So now we get onto the idea of measuring the mass of atoms. So we have to come up with a mass scale. So what we do is we define that a carbon 12 atom has a mass of 12 atomic mass units, and we define every other atom as either having a mass that is either a multiple or a fraction of that number. So we can now define the mass of any particular atom independent of its number of neutrons or protons. But these are not the numbers that are listed. The numbers that are listed in the periodic table are not for a single isotope, but rather they are an average weighted over all of the isotopes that are present in an actual sample. So I'm going to use boron to illustrate this idea. So boron naturally is comprised of boron 10 and boron 11, with 19.9% of boron in an actual sample being boron 10 and 80.1% of boron in an actual sample being boron 11. So boron 10 has 5 protons and 5 neutrons in its nucleus, and boron 11 has 5 protons and 6 electrons in its nucleus. The mass of a boron 10 atom is approximately 10.01 AMU, and the mass of a boron 11 atom is approximately 11.01 AMU. To calculate the average atomic mass, that is the mass of an average atom of boron in an actual sample, we take the mass of boron 10 multiplied by the fraction of it that is present in an atomic sample, in an actual sample. So to get from the percentage to the fraction, we have to divide by 100, and then we add, and then we do that for every other component and add them together. And so in this case, it's only 2 components, so we only have to do it twice. The mass of boron 10 times by its abundance plus the mass of boron 11 times by its fractional abundance. Add those 2 numbers together, and it gives us the average atomic mass of an average atom in an actual sample of boron, which comes out to be 10.811 AMU, in agreement with the periodic table. So we got it. Okay. So now we're going to talk about the periodic table, and the periodic table is extremely useful. So where does it come from? Well, through the 18th and 19th century, there were many new elements discovered, and it was recognized that it was a really difficult task to memorize the properties of all of the individual elements. So if there was a way of organizing them such that the properties were arranged in a systematic fashion, then that would make things a lot easier. So perhaps the most successful at doing this was Dmitri Mendeleev, and he organized the elements such that those with similar and chemical properties were placed next to one another. So in a fairly simple sort of process, he wrote what he knew about each element on a piece of card, and then he shuffled those cards so that the elements with the most similar properties were adjacent to each other. And what Mendeleev noticed was that after a while, the properties of the elements would repeat. It wasn't just a long line of elements, but they would repeat in a periodic fashion. And this periodic repeating of the properties of elements, we now call that the periodic law. That is, the properties of elements periodically repeat. Now, Mendeleev knew nothing of subatomic particles, but what we now recognize is that Mendeleev was arranging elements in order of atomic number. So Mendeleev was very wise, and he recognized that every now and then there would be a big gap in the properties of the elements, and he proposed that those gaps were where new elements would be discovered, and that they would fit into those gaps. And he also predicted what the properties of those elements would be. And so people set off to see if they could find, or perhaps not find, and then disprove Mendeleev's these elements that Mendeleev proposed were missing. So one of these elements was an element called that he called aluminum, which means near aluminum. And then 17 years after Mendeleev's table was proposed, scientists discovered this missing element and they named it gallium. So it's of interest to compare the properties of gallium that are observed experimentally with those predicted by Mendeleev. So Mendeleev predicted that the melting point of gallium would be low, and it's 20 degrees Celsius, which is room temperature. He predicted that the density of the gallium would be 5.9 grams per centimeter cube, which it is observed to be. And he predicted that gallium, or what he called eco-aluminum, would react with oxygen in a 2:3 ratio, and sure enough, gallium reacts with oxygen in a 2:3 ratio. So amazingly successful. So now, because we have an arrangement of the elements in order of their properties, we know that elements in any one region of the periodic table will have similar properties. So we just need to remember how the properties of the elements vary across the periodic table, as opposed to remembering the properties of each individual element. So the periodic table is divided into groups, which are vertical columns, and periods, which are horizontal rows. And you'll see that the groups are labelled in two ways, either 1 through 18, which is the modern labelling, or they are labelled with Roman numerals. Now, the Roman numeral labelling, you can see that there are A groups, 1 through 8, and then there are B groups, which run also 1 through 8. So the groups with an A in their name, they make up what are called the representative elements, and we're going to spend a lot of time talking about those elements. So the most important thing to recognize is that elements that are in the same group have similar properties. In the middle of the periodic table, we see these groups that have a B in their name. These are groups 3 through 12, and these are called the transition elements. Now you'll notice that it's a little discontinuous. It goes from 57 to 72, that's the atomic number, and then 58 to 71 is placed underneath, and then we see at actinium it goes from 89 to 104, and that's because 90 to 103 are placed underneath. This block, this what we call inner transition elements, is most commonly extracted from the periodic table, and the periodic table pushed together so it fits conveniently on one page. These two rows that appear underneath the periodic table, they do not have a group designation. Okay, so the periods are labelled, that's the horizontal rows, are labelled 1 through 7, and it's important to remember that this block that's underneath these inner transition elements, they actually belong in periods 6 and 7. So it goes 1, 2, 3, 4, 5, 6, 7, and then these guys are 6 and 7. Properties of elements show much greater variation across a period than down a group. So if I was to look at lithium and potassium, the variation in properties would be quite small, but if I was to look at lithium and boron moving the same distance across a group, across a period, the variation in properties would be quite large. So most of the periodic table, the entire left 2/3, incorporating group 1A and all of the transition elements and the inner transition elements, all of these elements in this sort of, I guess it's lavender, is that color? These are all metals. And then separating the metals from what we call the non-metals are the semi-metals, illustrated in green here, or they're sometimes called the metalloids. And then the upper right corner of the periodic table are the non-metals. Now hydrogen is a non-metal, but it is often placed either by itself or over on the far left of the periodic table, but it's important to recognize that hydrogen is a non-metal. So the metals have the following properties. They are all, at room temperature, they're all solids except for mercury, which is a liquid. They have a metallic luster, that means that they are shiny. They conduct electricity and heat well. They are ductile and can be drawn into wires. And they are malleable and can be pressed and bent into complex shapes. Some of the groups of the metals have special names. Group 1A is called the alkali metals because when they are placed in water it makes it alkali. Group 2A are known as the alkaline earth metals because when soil containing those elements is added to water it makes it alkaline. The inner transition elements, which are in periods 6 and 7, and the top row are known as the lanthanides because they come after lanthanum, and the bottom row is known as the actinides because they come after actinium. All of the elements in period 7 are radioactive and undergo radioactive decay. All of the elements beyond uranium are artificial or man-made. So the nonmetals occupy the upper right corner of the periodic table and also include hydrogen. Nonmetals have the following properties. Those that are solids are dull and brittle. They tend to crumble and not be shiny. They are poor conductors of heat and electricity. Most are solids or gases but at room temperature, but bromine over here is a liquid. All of the members of group 8 are nonmetals and are gases, and these elements are referred to as the noble or inert gases, and except for under unusual circumstances they don't interact with other elements. That's where they get the title of noble from. They don't interact much with the sort of more common elements. Group 6A, or group 16 in the modern naming system, this is called the oxygen group or the chalcogens, and they are all solids at room temperature with the exception of oxygen. Group 7A, or 17 in the modern naming system, is known as the halogens, and fluorine and chlorine are gases. Bromine, as we already discussed, is a liquid, and iodine and astatine are both solids. So the metalloids separate the metals from the nonmetals, and they line up on this sort of staircase line that falls down here, and they have properties that are intermediate between the nonmetals and the metals, and they are all solids at room temperature.